Today's lesson is going to be on Gibbs free energy, which is delta G. And this is another thing that we can use to determine if a process is thermodynamically favorable. So the maximum amount of energy available from any chemical reaction is going to be our delta G. There's two forces that drive our chemical reactions. The enthalpy, which is our delta H, and that's the change in potential energy between the reactants and the products, or it would be products minus reactants, and the change in entropy, which is our delta S. So the sign for delta G is going to allow us to predict if the overall reaction is spontaneous at equilibrium. All right, so sodium reacts violently in water. So sodium metal, we don't even have any sodium metal in our stockroom because it's so reactive. But if we were to order it, which we can't, but if we were to order it, it would come in an oil because even the water in the air around us is enough to make this sodium be a violent reaction. And I mean, it's like an instantaneous explosion almost. So sodium is actually sent to labs that need to use it for whatever reason in oil. So how are we going to calculate delta G? To calculate delta G, we're going to use the same formula we used for delta H, and we're going to use the same formula that we used for delta S. Okay, so it is the sum of the number of moles of the delta G formation of products minus the sum of moles of the delta G formation of reactants. So the delta G of formation is the change in energy when 1 mole of product is formed. So again, we're looking at mole dependent. We're doing it per mole formed. Now, if delta G is greater than 0, meaning it is positive, then it is not thermodynamically favorable. If delta G is less than 0, meaning negative, it is a thermodynamically favorable process. So let's stop right here. Delta H is thermodynamically favorable if it is negative. Delta S is thermodynamically favorable if it is positive. Delta G is thermodynamically favorable if it is negative. All right, so keep that in mind. So here we go. Let's calculate the delta G of the following equations. We have 1 mole of product here, so our formula is the same, and we're going to go to our reference tables, and we're going to look up the delta G values. Now notice here the delta G value of the hydrogen and the chlorine are both 0, just like they were for the delta H, okay? So our delta G for our standard states is also 0. So when we plug it in, we get a negative 95.31, and you'll notice this is in kilojoules per mole. Because this is negative, this is a thermodynamically favorable process. Let's stop again. Delta H is measured in kilojoules per mole. Delta S is measured in joules per mole, and delta G is measured in kilojoules per mole. And now this is going to be important because there is a relationship between all three of these. We haven't talked about it, but there is. There's a relationship between all three of these. So if we're calculating relationships, you'll notice there is a change in units, kilojoules, joules, kilojoules, and you can't put apples and oranges together, so you have to have kilojoules or you have to have joules, but you can't have both. All right, so we'll get to that, okay? Just keep this in mind. So for our next reaction, let's calculate the delta G. The delta G value here, we're going to plug in our value. So calcium carbonate is negative 1128.8. minus the sum of the reactants. So calcium oxide solid is negative 604.2 and carbon dioxide gas is negative 394.36. So that gives us a negative 130.24 kilojoules per mole. So you'll notice in this, between all of our different videos, we have now calculated the delta H, the delta S, and the delta G for 2 equations. So here's our relationship between the 3 different parts. Delta G, this is our change in free energy, the amount of maximum energy needed to do work. Our delta H is our change in enthalpy. This is the heat transfer. Our delta S is our change in entropy. All right, how does the disorder of a system change? This is in joules. Delta H is kilojoules and delta G is kilojoules. T is our temperature. All right, so if we were to take T times delta S, all right, that is the overall amount of energy used to create a change in entropy. So let's use Gibbs free energy to calculate delta G of the following and then determine if these are spontaneous processes. So we've already determined the delta H and the delta S values for both of these reactions in earlier presentations. So just go back to your notes and look up those values. So delta G equals delta H minus T delta S. So my delta H we've already determined to be negative 92.3 kilojoules. My temperature, it tells me, is at 298 Kelvin, all right? And my delta S value, we found it to be in joules, so I've converted it to kilojoules. So I took my delta S value and I converted it to kilojoules so that we had kilojoules and kilojoules. And I wanted to convert my S to kilojoules because my G is always in kilojoules. So it really makes no sense to convert my H into joules because then I'm going to have to do a second conversion to get it back into kilojoules. And we like to try and minimize the amount of work required. So just calculate your delta S, put it in kilojoules. So when you solve for this, you find an overall negative 95.3 kilojoules. This is a spontaneous process. The formation of hydrochloric acid will happen spontaneously without the help of any outside sources. All right, let's check out our next equation. So again, here's my delta H value. Here is my delta S value in kilojoules. We found it in joules. I just converted from joules to kilojoules here. All right, and again, these 2 values came from previous notes. So when we solve, we get a negative 130. So again, this is a thermodynamically favorable process. So let's look at the favorability of reactions in relationship to the temperature. And again, our delta G equals a delta H minus T delta S. So if I have a negative delta H and a positive delta S. Temperature times a positive, a negative T times a positive is overall negative. A negative minus a negative gives me a negative delta G, so I am thermodynamically favorable at all temperatures. See how I worked that out? So I like to use logic to figure these out. Instead of trying to memorize it, I like to think about it. Okay. If delta H is positive, delta S is negative. So negative T times a negative overall is positive. A positive plus a positive give me a positive delta G. So I am not thermodynamically favorable at any temperature. So in this case, that system would need something to get it going, all right, because it's not going to happen on its own. A negative delta H and a negative delta S. A negative times a negative is a positive. But if my delta H is larger than my T delta S, Like, for example, let's say my delta H was 400 and my T delta S was a positive 200. Overall, that gives me a negative 200. So at that temperature, I am thermodynamically favorable. So in this case, we are dependent on temperature. All right, if the temperature is low enough that it gives me a T delta S that is small enough of a value that my H is greater, then it is still going to be thermodynamically favorable. If my temperature is a very high value, then a positive, like let's say delta H is negative 400, and my T delta S, my temperature is high, so let's say that was 600. And I'm just making these values up. They don't really make sense. We're just doing it as a get the logic behind it. So that gives me a positive 200. So at a high temperature, not thermodynamically favorable. So let's do our final one. All right, what if I have a positive delta H value and a positive delta S? A positive delta S and a minus T, so minus times a positive is a negative. So again, temperature is dependent here. If I have a large delta H value, and we'll just go back with the 400, and let's say my T delta S is a negative 200. At that case, whoops, 400 minus 200 is 200. At that case, my delta G is positive, and I'm not thermodynamically favorable. So at this case, I am only going to be thermodynamically favorable if the temperature is high. This T delta S value has to be high enough that it overcomes the positive delta H. All right. And I think it's down here. Yeah, okay. And we're not thermodynamically favorable at low. I'm sorry, I left that out. So in the particular reaction, delta H is positive and delta S is negative. Is this spontaneous? So delta H is positive and delta S is very negative. All right, so a negative times a negative is a positive value. So a positive plus a positive is a positive delta G, so it is non-spontaneous.